Hello everyone and welcome back to FatalSec. Today in this video we are going to look at different addressing types that we have in ARM as well as in other assembly languages. So the general idea behind addressing mode is that there are ways in which we are able to store and load the data from various memory locations that we have, including registers. So for example, in the last video we have written this simple exit program in which we have used these move instructions to move a constant value, right? This type of addressing mode is called immediate addressing mode. So in immediate addressing mode, it basically allows you to specify an immediate or a constant value directly within an instruction, right? Or in other words, the CPU or the processor does not have to look into the memory or the registers for the operand value. Instead, it's encoded in the instruction itself. Let's break it down. Consider this block diagram. Over here, we have divided our instructions into three parts. First one is called the opcode, which is move in this case. Opcode tells the processor which instruction it is. Then the next part of the instruction is called operand. There could be more than two operands as well, but for this instruction we have only two operands. First operand will tell the processor where to store the data. So this is going to be our destination register or the destination operand. For example, here operand 1 is telling to store the value into X0 register. Then we have our second operand, which is telling the processor what value exactly to be stored. Now to tell the processor that here we are going to store a constant value directly into the register, we have to add this hash symbol in front of the value. So whenever you want to store a constant value, always put this hash symbol in front of your operand. Based on this, processor will decide whether it's an immediate addressing mode or not. Similarly, we can use this move instruction to move values between two different registers. For example, consider this move instruction move x0, x1. Here we are moving value of x1 register into x0 register. Okay. This is called register direct addressing mode because here we are moving value directly from one register to another. So for example, let's assume that x1 register is containing hex 3D. Now can you guess what will happen when this instruction is going to be executed? Yes, the value present in the x1 register, which is hex 3D, will be stored into our destination register, which is x0, right? So to demonstrate this, let's create a simple program in ARM assembly and let's name it as direct mode.s. Okay. Again on the top, we are going to use our global declarative to declare the global symbol. Then we will create our text section, and inside text section we are going to define our start label. So based on our example which we just discussed, we are going to move hex 3D into x1 register, right? So for that we have move instruction followed by operand 1, which is going to be our destination register, which is x1, right? And then we want to store hex 3D into that, right? So this is our register immediate addressing mode. Okay. Then we are going to store the value of x1 register into x0 register. So for that we have move again the destination register, which is x0, where we want to store the value, followed by operand 2, which is the source register from where we want to copy the value, which is x1, right? So now this instruction is our register direct addressing mode. Here we are moving the value directly from one register to another. And in the first instruction, this is our register immediate addressing mode, where we are copying a constant value into a register, right? And then just to exit the program normally, we are going to use the exit routine which we have created in the last video. Let me just copy that. So this will tell the processor to exit the program with the exit code 54, right? If you haven't checked out our previous video where we have explained the exit program call and these move instruction, then do check it out. All right, so let's save this program now and compile it using arcgnu assembler followed by the name of program file, which is direct mode.s. then the name of our output file, which is direct mode.o. So like I mentioned in the previous video, the assembler will generate an intermediate code or an object file first, and then we have to use another program or the tool called linker. Then this program will take this object file, okay, as input, and as output it is going to generate the final executable. So now you see we have our object file and our executable file, right? So if we try to execute this direct mode executable directly, we are not going to see anything, but we have used an exit routine which is going to set the exit code to 54, right? So we can quickly check what is the exit code we got. It's 54. So this means our program executed normally. And let's see how these two addressing mode is going to look like during the execution. So for that we are going to use GDB debugger, and let's give it this executable, enter. So now the binary is loaded into the GDB, and now we have to look into the disassembly of this binary to figure out the address of the instructions where they are loaded. For that we have disassemble command followed by the label, which is start, enter. Now you see these are the instructions which we have coded, right? So the first instruction is actually loaded at this address. So let's put a breakpoint over here using break followed by the address. Now the breakpoint is set at this address, and now we can execute this binary in the debugger using start command. Hit enter. As you see, it's breaking at this address, which is our first instruction, and as of now all the registers are initialized with 0, right? And our program is waiting at this instruction. So this move x1 comma hash x3d is our immediate addressing mode, which is going to store this constant value into x1 register. So let's see, currently x1 is containing 0, right? So after executing this, let's see what happens. Step I. So this instruction is executed, and now the program is waiting for this instruction to be executed, and now our x1 is modified with hex 3d, right? So the immediate or the constant value is now stored into the x1 register. Now let's see what's going to happen when we execute our next instruction, which is move x0 comma x1. So to execute this instruction, we have to tell the debugger to step further using step I command. Now this instruction is executed, and let's see what happened with x0 register. So as you see, now x0 register is modified with the value of hex 3d, right? And that's because it has copied the value of x1 register into x0, right? So whatever the value present in x1 register during the execution of this instruction, that will be moved or copied into x0. So at this time x1 was having the value of hex 3d, which is copied into x0 register, right? So now you can tell by looking at the move instruction which type of addressing mode it is. So for example, this instruction is again our immediate addressing mode, right? Similarly this one also, and then we have our software interrupt, which is going to call the exit function call based on the system call number. Let's quit this program now. So these are the two type of addressing mode that deal with the register memory, and these are the most common ones that we will typically see when we are dealing with registers. Okay. Now there are some other interesting addressing modes which deals with the data stored in the memory or at certain memory addresses. So to demonstrate this, first I am going to go ahead and show you how to store the data onto the memory, and then we will take a look at how we can work with the data that is stored in the memory. Okay. To do this, we have to use the data section in our binary. A binary is normally divided into multiple segments, one of which is a data segment which contains the constants and variables used by the program, right? During the execution, what happens is that operating system allocates the memory for this data section. So let's program it in our assembly code. Let's create another file and name it as indirect mode.s. Okay. So to define the data section, we have to use data directive, and under this directive, we can declare any data that we want to put onto the memory. So in order to declare the data, we first have to make a label. You can think of this as declaring a variable in high level programming language and assigning a value to it. So for example, in C, to declare an integer data, we first create a variable name of the desired data type, right? And then we assign a value to it. So consider this piece of code. Let me comment it out so that it won't interfere during the compilation. So this piece of code is basically telling the processor to store 100 value, which is of type integer, right? So we have defined our variable as type integer, and then during the execution it will store 100 value into this, right? So let's try to replicate this program into assembly. So what we have to do is, so firstly we have to declare our global declarative, which is dot global underscore start. Then we are going to declare a new section called dot section dot data. Now inside this declarative we have to create a label which is myvar. Okay, so this label you can consider it as a variable, and then we will assign an integer value to it. But if you remember from the last video, I explained you that in assembly we don't have data types such as integer, float, string, right? Rather in assembly we have data types such as word or half word. Now it depends on the size of the data you want to store. For example, here we are trying to store 100, which is an integer. So integer basically takes 4 byte, which is 32 bits. So we can use half word in this case to store a single integer value. Okay, you can even use the full 64 bits of the register by defining it as dot word, but then the rest of the 32 bits will be wasted. So let's define our label and assign a value to it. Okay, we have defined our label here with the name myvar, and inside this we are going to tell the size of the data we want to store, which is half word in this case, which you can denote using .h word. Okay, and then the value, which is 100. All right, now this piece of code is equivalent to this C code. So you must be wondering that this data we have hard coded into the binary, how will this be stored in the memory? Well, when we execute any binary or executable, the whole executable gets loaded into the memory by the operating system. So when we execute this binary, this data section will be there somewhere in the memory. Okay. However, this is not it. We have to tell the CPU where in memory this data is stored so that we can use it later to do further processing. So as you know that CPU only knows what's there in the registers. So to tell the CPU where this data is actually in the memory, we have an instruction called ADR. So now we are going to write the instructions which comes under .text section. So let's define our text section here. And inside this text section, we can define our start label. So the first instruction we are going to use is ADR instruction. So now what we are going to do, we are going to assign this 100 value into our general purpose register. So here I am going to use X0 as our destination register. You can use any other general purpose register for this purpose. Okay, so X0 is going to be our destination register, and then I want to store the value which is present in my var label. So to tell, so the second instruction is going to be our label, which is my var. Okay, so now this ADR instruction is used to load the address of the label into the register. Okay, what this means is that it is not going to store directly the 100 value into X0 register. Instead, it is going to store the address where this my var variable or label is defined in the executable. If it's not clear yet what it is going to do, don't worry, we will see it in action when we debug this program. Okay, now to access the value of this label, we have another instruction called LDR, okay, which stands for load register. Let's code this first. So LDR followed by our operand 1, which is the destination register. So like I mentioned, the size of the data which we are going to store is of half word size, right? So to denote or to tell the processor to use only the lower 32 bits of the register, we can use W followed by the register number, let's say 1. Then in the square brackets, we are going to put our source register, which is X0 in this case. So over here, we are telling the processor to load the value which is present at the memory location pointed out by this X0 register. Okay. This type of addressing mode is called register indirect addressing mode, because here we are not directly storing the value which is stored in X0 register. Instead, we are storing the value which is pointed out by the memory location which is stored in X0 register, and then that value will be stored in W1 register, right? If it's not clear yet, let's further break it down. So in this case, LDR is our opcode, W1 is our operand 1, and X0 within square bracket is our operand 2. Now you see that the X0 register is containing value hex 10,000, and if we look at this memory location, it contains hex 64 value, which is nothing but 100 in decimal. So how this instruction is going to be executed? First of all, operand 2 will be resolved. So the processor will look into the value stored in X0 register, which is a memory location hex 10,000, right? Then the processor will look at this memory location in the memory. So in the memory at hex 10,000, we have hex 64 or 100 in, right? So this 100 will then be stored into W1 register. Okay, coming back to the program, let's again copy this exit routine and paste it over here to tell the program to simply exit the execution. Let's save it. And now we need to compile it again using ARC Linux GNU assembler and the name of our file, which is indirectmode.s. Then we can specify the output name, which is indirectmode.o. And then we have to finally generate the executable using the linker. So this will take our indirect mode.object file and it will generate indirect mode as the executable. So now we have a program or a executable called indirect mode. Let's see this in action by debugging it using GDB. So GDB followed by the name of the executable, which is indirect mode. Reading symbols from indirect mode, which means the binary is loaded into the debugger. Let's see the disassembly using disassemble underscore start command. So this is the disassembly and the first instruction is loaded at this address. So let's copy this and attach a breakpoint over here. Breakpoint is set to this address now, so we can start executing our binary in the debugger now. Enter. Again, all the registers are initialized with 0. And our first instruction is ADR X0, and you see now that our label myvar is changed to this address, right? So what assembler did was it replaced the myvar label with the memory location, right? So now this ADR instruction will load this address into X0 register. Let's see. Step in, and yep, you see the X0 register is now containing this memory address, right? So let's see what's the value inside this memory address. So to examine the memory, we have a command P to print the value, followed by X to examine it, followed by the memory location. Enter. You see this memory location containing hex 64, which is nothing but 100 in decimal. So just to clarify what happened over here, our myvar label, which we have used in this instruction, got resolved and replaced with the actual memory location, which is 4100C4 in this case, right? Then this memory location is stored into this X0 register. So now our X0 register is pointing to a memory location which is containing hex 64 or 100. Then coming to the next instruction, which is LDR W1 comma X0 in square brackets. Let's first execute it using step I command. And now let's have a look what happened with W1 register. So you see X1 register is now modified and containing hex 64, which is the value present at this memory location, right? So what happened? Our X0 register was having a memory location which is 4100C4. These square brackets told the processor to look into this memory location instead of directly copying the memory address into W1, right? So whenever you see a square bracket in your instruction, you can immediately think of it as a pointer in C, right? Similarly over here, these square brackets are telling the processor to look at the value which is present at the memory location specified by this register. I hope it's clear. Then we have something called register indirect with offset addressing mode. To showcase this, instead of storing a simple integer value, we are going to store an array or a list of integers into the memory. So let's create a new program called indirect offset mode.s. As usual, again we are going to define our global declarative, and since we want to store the data again, we are going to use the data section. So let's define our data section using .section.data. And now to demonstrate the register indirect with offset addressing mode, I think the best way is to show you how to store an array of items. So let's consider this piece of code in C. Int array is equal to 10, 20, 30, 40, 50. Okay, let's say we want to store these integer values into an array. So again, just like what we did in the previous example, first we have to declare our label or the variable name, which is ARR in this case, right? And then we have to tell the size of the data which we want to store into the memory. So now important thing to note here, you can either use half word or word. This time I am going to use the whole 64 bits of the register, so I am going to define it as dot word followed by the values which I want to store. So 10, 20, 30, 40, 50. Then let's define our dot text section. Over here we are going to define our start label, and then let's start writing the instructions. So first of all, again these values which we have hard coded here, they are in the data section of the binary, right? And to access these, we have to store the label into one of the general purpose registers, right? Because processor cannot directly access the memory, it has only access to the registers. So we have to store the value or the address into the register first, then only the processor can act on it. So using the ADR instruction, again we are going to store the address of our label, which is ARR. Again I am going to use X0 register for this purpose, followed by the operand 2, which is the name of our label, which is ARR. Okay, so this instruction will store the memory address of this label into X0. Then what we want to do is to access this first item from the list of integers, right? So for this purpose, let's use LDR instruction followed by the destination register, which is, let's say, W1, then X0 in square brackets. So now you can tell what type of addressing mode it is, right? This is register indirect addressing mode because we are telling the processor to actually access the value stored in the memory location pointed out by the X0 register, and that value will be stored in our destination register, which is W1. Now I have used W1 here because I know that the size of the data which I want to access is actually not more than 32 bits, right? So this is nothing new, this is exactly what we did in our last program. What I want to show here is the use of offsets. So in C, to access a particular item from the list of arrays, we do something like this, right? So this one basically tells which item to access. For example, one will tell the processor to access this 20 value. The indexing starts from 0, so at 0th index 10 is present, at first index 20 is present, and so on. Similarly, to access any other value, we have to add certain offset to the address pointed out by our ARR label, which is now present in X0 register. And this is where register indirect with offsets come into the picture. To understand this, so let's assume that we want to access this first item 0, 1, right? From this list, what we have to do is we will add certain number of bytes to the memory location pointed out by our array label. So by default, if we access the value present at this memory location, it will give us the 0th index of this list, which is 10, right? So this instruction in W0 will be containing the value at 0th index, which is 10. Right now we want to access this value which is present at the first index. So to do this, you have to remember one thing, which is that in ARMv8, even though it's a 64-bit processor, each memory location can only store 4 bytes. So the memory is always byte addressable, and to access this next location or the next index, we have to add 4 bytes to the memory location, right? Similarly, to access the second index, we have to add 8 bytes, and so on. So again, to access the first index, we are going to use the LDR instruction. This time I want to store this value into W2 register. Then our array label, we are going to tell the processor to look into the memory location stored into X0 register, and then inside these square brackets itself we can pass the offset, like how many bytes we want to add to this memory location. Okay, so here we want to add 4 bytes to access this 20. This is called register indirect with offset addressing mode. Similarly, let's also try to store this second index into W3 register. So for that we can tell the processor by adding 8 bytes, right? And then let's simply copy this exit routine to exit the program normally. Okay, so again in this LDR instruction, first the addition operation is going to be performed, and then that memory location will be resolved, and whatever the value present at the new memory location will be stored into our destination register, right? If it's not clear yet, let me try to break it down using this block diagram. In our second operand we have x0 comma hash 4, right? So what's going to happen is that it will first look into the x0 register. So over here in x0 register we have hex 10,000, right, which is a memory location. So it will pick that value and do an addition operation with our immediate value or the offset we have passed over here, which is hash 4, right? So if we add 4 bytes to this hex 10,000, the result will become hex 10,004, right? So this hex 10,004 will then be used as the source memory location, and the processor will look into this memory address. Now at hex 10,004 we have hex 20 value. So this value will be picked up from the memory and it will be stored into our destination register, which is W2, right? Let's see this in action as well. So first of all, let's compile the code using the assembler. Then we have to use the linker. Okay, so now we have our indirect offset mode binary. Let's try to debug it. Reading symbol from the indirect offset mode. So our binary is loaded, and let's see the disassembly using disassemble start command. Right, you see our array variable is replaced with the actual memory location after the binary is loaded into the memory by the operating system. So this first ADR instruction is simply going to store this memory location into X0 register, right? Let's see. Okay, we have to first start the program, and now let's tap into it and see what is the value in X0 register. So you see X0 register is now containing this memory location, right? Then this is our indirect addressing mode, and this will store the value present at this memory location into W1. So let's examine what's the value present at this memory location first. It's hex A. Hex A is nothing but 10 in decimal. This is the value we have at the 0th index of our list, right? So the 0th index will be stored into W1 register. Let's tap into it and see now what X1 is containing. X1 is now containing hex A 10, which is the first value in our list. Now coming on to the next instruction, which is our LDR W2 comma X0 comma hash 4 within square brackets. So like I mentioned, first of all it will add 4 bytes to the memory location pointed out by X0, and in X0 we have this address, so it will add 4 bytes to this memory address. One thing to note here is that it will not replace the value of the X0 register. It will simply add it, keep it in the cache, and then resolve that address and store the value into W2 register. Alright, so let's first try to resolve this manually. As we just saw, X0 is now containing this memory location, right? Let's copy it and open the calculator application. Make sure your calculator is in the programming mode, and this output value is set to hexadecimal. So let's paste this value over here and add 4 bytes to it. Okay, so after adding the 4 byte, the new memory location became 4100D0. Let's copy it and examine it. p/x at this location. So you see this location is containing hex 14. So hex 14 is nothing but 20 in decimal. And after executing this instruction, this value got resolved to this memory location, and then these square brackets told the processor to look at this memory location in the memory and copy that value into W2 register. Let's see. W2 or X2 register is now containing hex 14, which is 20 in decimal, right? Similarly, let's try to resolve this. So what this particular thing will do, it will add 8 bytes to the memory location pointed out by X0 register, and the X0 register is pointing to this memory location. So let's copy it again, go back to the calculator, change it to hexadecimal and paste this value and add 8 bytes to it. After adding 8 bytes, the new memory location became 4100D4. Let's examine it. Okay, at this memory address, our value is hex 1E, which is nothing but 30 in decimal. So once we execute this instruction, the W3 register is now containing hex 1E. Let's see. Yes, X3 register is now changed to hex 1E, which is 30. So similarly, you can access all the values present in the array. Okay, let's quit this program. I hope this is clear because we still have two more addressing modes, and these two addressing modes are very much similar to this one, which is register indirect with offset. So the next addressing mode is called pre-indexing mode, and to understand this mode, let's first try to create a new file with the name indirect pre-index mode.s. okay, dot global start. Again, let's define our data section, and inside it let's define our list 10, 20, 30, 40, 50, right? And then we have our text section where we will define our start label, right? Just like what we did in the previous program, let's store the address of our label into X0 register like this. Now this time we are going to use pre-indexing mode. So for that we are going to use LDR register again, followed by our destination register, let's say W1, followed by operand 2, which is going to be the memory location from where we want to copy the value. This is going to be X0, and let's copy the first item from the list, which is this one, right? So we have to add 4 bytes to it, and to tell the processor that we want to use the pre-indexing mode, we will simply add this exclamation mark. So what exactly it's going to do, let's see. So the whole instruction will work just like our previous mode, where it's adding 4 bytes to the X0 register, and then whatever the value present at that new memory location, that will be copied into W2 register, right? So there is no change in that. Only one additional step is added, which is to store the result of the addition into X0 register. So if you remember from the previous example, after adding these 4 bytes, the value in the X0 register was not modified. For example, here the X0 register was containing hex 10,000, and after adding 4 bytes to this X0 register, the new value became 10,004. So you can consider this expression as X0 equal to X0 plus 4, whereas without this exclamation mark previously it was only X0 plus 4. I hope the difference is clear now. So now let's copy the exit routine, save and assemble our program, and then we are going to use the linker from the object file, right? So now we have a new executable called indirect pre-index mode. Let's see this in action. Indirect pre-index mode. So the binary is now loaded into the debugger. Let's see the disassembly of it. All right, so I'm skipping over this instruction because I hope it's clear now what it's going to do. First of all, we need to start the program, and then let's step over the first instruction. Okay, so after executing the first instruction, X0 is now containing this memory location, right? And then let's see what this instruction is going to do. So like I mentioned, firstly it will add 4 bytes to the x0 register, and then this exclamation mark will tell the processor to store the result of this addition into x0 register. So let's see this. If we step over this instruction, now our x0 register should be having the updated memory location instead of this one, and in the W1 register or X1 register, it would be containing the value pointed out by the updated memory location. So let's see. If we look into the registers, X0 value has changed to 4100C8, right? Earlier it was pointing to 4100CC, right? Then our X1 register also got updated, and it's now containing hex 14, which is 20 in decimal. Cool. So whenever you see the exclamation mark along with indirect offset addressing mode, you can tell that it's using pre-indexing. Okay. Similarly, we have another addressing mode called register indirect post-index mode. This addressing mode, as the name suggests, will do the increment to the value after doing the main operation. For example, consider this block diagram. Over here, if you look at the instruction, now we have 3 operands. So what will happen is that firstly, it will look into the x0 register. So here our x0 register is containing a memory address hex 10,000, right? Then it will load the value present at this memory location into the destination register, which is our operand 1, right? So this hex 10 will be copied to our destination register W2. Okay. And after that, it will do the increment to the memory address of x0 register. So it will add 4 bytes to this hex 10,000 and update the register value. Okay. So to demonstrate this, let's again create a new file called indirect post index mode. Okay. Global start. We have our data section where we are going to define our label 10, 20, 30, 40, 50. Then we have our text section where we will define our start label. So first of all, using ADR instruction, let's store the address of the label. Then using LDR instruction, we are going to tell the processor to use post indexing mode. For that, the first operand is going to be our destination register, let's say W1, followed by operand 2 from where we want to copy the value which is pointed out by x0 register, followed by the operand 3 which is going to tell how many bytes to add into the memory location. Let's say we want to add 4 bytes. Let's copy the exit routine again and save our program. Let's compile it using the assembler. Linker. So now we have our indirect post index mode binary. Let's quickly load it into the debugger. Okay, and let's see the disassembly of it. Let's start the program in the debugger. So I'm going to step over the first instruction, which is going to copy the memory address of our label into x0 register. And then what's going to happen is that first of all, it will store the value pointed out by the memory location stored into this x0 register to W1. Have hex A 10, right? So this 10 will be stored into W1, and after that this memory location, then after that 4 bytes will be added to this memory location, and after adding 4 bytes the new memory location will be stored into x0 register. So let's step over it and see the changes. Let's see. So now you see in the x0 register it's updated to 4100C8, right? Initially in x0 we had 4100C4, so it added 4 byte to it and stored it into x0 register. But before doing this operation, what it did, it stored the value pointed out by the memory location present in x0 at this time, okay, which was hex A, right? Cool. So in this lesson we have covered different addressing modes that we have in ARMv8 architecture, and in the next lesson we are going to have a look at various arithmetic operations such as add, subtract, multiplication, And also we'll see the role of our special register called SPSR register, which contains various flags such as carry flag, overflow flag. Thank you so much and stay tuned for the next lesson.